You mentioned it at the beginning. Obviously, QC is on its journey. What's being done in relation to improving kind of qubit stability and error correction within QC?
Yeah, that's very very good points. That's the sort of main, I guess, engineering hurdle, and there's two aspects to that. There's the hardware aspect and the software aspect. So the hardware aspect is you've got to think of ways that you build more robust qubits. That can come down to having better isolated environments for your qubits, or that can come to down to how you sort of design these the actual qubits themselves and how you connect them in some sort of way. And basically, you want to mitigate what are called sort of like loss channels. Essentially, you want to reduce them as much as possible and keep them well isolated and have them only interact with the signals that you're inputting and outputting as well. So that's sort of one aspect of improving the hardware to making sure that's as robust as it possibly can be. And then the other aspect is there's a whole software, effectively research side around quantum error correction, which is a huge field, very complex. And that is essentially trying to say, okay, we have some sort of noise and we know that the qubits may decohere or have a bit flip at some point in the calculation. How do we put code on top of that that can account for those errors and mitigate in software the response that we're getting? And this is where you may hear these terms called like you have physical qubits and logical qubits. The physical qubit is the individual device that you have that's tiny, it's microscopic on your chip, or it's an individual atom or ion, depending on how you build your quantum computer. But you can add more around them, sort of ancillary qubits, to create what's called a logical qubit. And that is essentially a bunch of qubits acting as if it was one, where if one falls over or one has an error or some sort of like phase flip or bit flip, the others can pick up the slack almost. And then it's how you build those error correction codes on top of these sort of logical qubits as well. So there's a lot of push in big tech companies to create a really solid logical qubit. I think the best known example I have to see this is IBM. They've been building quantum computers for years now, and they published their roadmap. And I can't remember the numbers exactly, but they're saying they want to get to a certain number of physical qubits by 2030, say, but what seems like a lower number of logical qubits, but they'll be much more stable and much more robust to do more interesting calculations with. So it's sort of two-horse race in the sort of bringing the two software and hardware sides together so that you can really build that in that true fault tolerance is what it's called in the industry as well.
Yeah,
And
so
it's not an easy problem to solve.
I was going to say, but I'm assuming that is fairly crucial, obviously, in the development of QC and actually seeing it in anger, kind of in
Oh,
the industry.
100%.
Yeah,
Absolutely, yeah. Because it's when you start seeing this fault tolerance is when you can start building these useful algorithms that can be applied to, like we mentioned earlier, the pharmaceutical industry or what we work on now in the financial industry. By having these, when you have these truly fault tolerant quantum computers, that's when you're going to start really seeing a game changing move. And we always talk about quantum computing will one day have its ChatGPT moment, right, where it will be suddenly in the public's imagination and suddenly everyone will care about it. So it will be around the time we can crack this fault tolerance with a quantum computer.
yeah, you can't really fathom how powerful potentially that could be, right? And how it could not only change certain industries, but I guess us affect us, the normal person day to day.
Yeah,
Everybody's using
absolutely.
kind of AI, whether it's on your desktop or using it for, I don't know, for delivering something to a client, and everything in between. So, yeah, I mean, God knows how powerful that could be, right? It's scary. So,
Yeah, it is scary, and I think a lot of discussion around this goes into sort of like regulation and ethics as well. So I think a lot of the regulators are sort of doing their fact-finding missions at the moment to try and understand the technology better, so they can regulate it so it stays safe and is used for the greater good than it otherwise would be, and make sure that they understand the technology as well. So I think it's a very crucial point.
yeah. So I guess that segues quite nicely into, I guess, AI, ML. In your opinion, how can quantum computing potentially revolutionize AI and ML? Yeah,
Yeah, no, it's a very very good point. It's what we spend a lot of our time working on currently. It's my employer as well. So there's two main ways that we would potentially see advantage in like AI and ML. And the first could be a speed advantage. So maybe you're able to train faster, or maybe you're able to get a result from your pre-trained algorithm faster if you want to, I don't know, do some sort of classification task or sort of prediction task, whatever that may be. And on the other side, what we're also seeing early signs of, and we need to explore a little bit further, is that we're seeing that we can potentially train algorithms or get our quantum algorithms to a similar level of, say, accuracy, precision, or whatever your metric is of performance, but being able to train on less data than you otherwise would for classical computers, because you have potentially this much larger information space available to you from a quantum computer. So that's the sort of two main ways we're potentially seeing advantage slowly coming from quantum computing at the minute. Obviously, the hardware, as we were discussing earlier, is still at this earlier stage, so we're sort of trying to increment where we can gain value now and gain sort of insights now to then build a sort of understanding that is ready for this moment of fault tolerance that will happen with quantum computing.
Awesome, awesome. Well, yeah, I mean that's super insightful, and I'd like to think any, I guess, rising stars within the QC world who may be tuning into this would hopefully have taken a couple of key pointers. Obviously, listening to your journey. So, if anyone does want to reach out, Shaun, directly, I guess LinkedIn's a good platform
Yeah,
to.
absolutely. I'm on LinkedIn. I post on
Yeah,
that every now and then. We'll probably post this podcast on LinkedIn, so that'd be great.
yeah,
Yeah, absolutely. That's the best way to get in touch.
yeah. Awesome. Well, absolute pleasure. Yeah, really appreciate your time, and thanks for coming on. And yeah, hopefully we can do this again sometime soon.
No, I hope so. It was really good. You asked some great questions, actually, and I think questions that are often asked, but also often not asked. So you need to get that full sort of encompassing picture, which is exciting to talk about.
Appreciate it, Sean. Thanks so much.
Thank you very much, Zach. I'll speak to you later.